All right. Well, hey, welcome to Calculus late night edition. Who knows when you're watching this, but since we are not having class on Friday morning, I decided to go ahead and record this lecture. So it's Thursday evening. We'll do a little calculus at night. So we've been talking about differential equations. We've seen what they are. We've seen what it means to find solutions, and we've even solved some, right? We've seen that we can solve ones that are first order, where we have y prime just equals a function of x. We just integrate both sides. Or if it's separable, which is one where we can get all of our y's on one side, all of our x's on the other side, then we integrate both sides and we're good to go, right? And probably the most basic separable we know how to solve is that nice, simple, easy y prime equals ky, right? Let me just remind you about that. So this guy, we saw that after you go through the steps, we end up with y equals c e to the kt, which was exponential growth. Pretty easy, right? So I'm not going to go over redoing that one, but we found that. Now, I want you to think about this in the context of the real world. Now, we talk about exponential growth applying to lots of different things, specifically growth of populations, like bacteria in a petri dish, deer in the Tahoe Basin, whatever it happens to be. But there's a bit of an issue if we use this differential equation to try to model a population. I mean, let's just go simple. Let's go bacteria in a petri dish. If we were to draw the graph of the solution, right, we were to say, all right, the population changes at a rate proportional to how many there are. You draw the graph of this thing, we're going to have whatever our initial value is, right? Our initial population, let's say it's, we'll go say y of 0 equals y naught. So we're here at y naught. And what this is going to do is just grow exponentially forever. And the problem with this model is that as time goes on, it doesn't make sense that the bacteria can just keep growing. Eventually, they're going to run out of space, going to run out of food. There's competition between the bacteria cells and so on, right? So eventually, it's going to have to stop growing. There's going to be a maximum number of bacteria that we could actually have in this petri dish due to the constraints, right? Well, let's introduce that. We call that value, that number, a carrying capacity. So what I'm going to do here is I'm just going to put a horizontal line, and let's introduce a carrying capacity. So that's what this value is. We're going to use the letter K to represent the carrying capacity. And I know what you're thinking. Let's just use a C. But remember, we use C a lot when we integrate, our plus C's. So just so that we don't get confused, we'll switch it to a K. So we'll just be really bad spellers, right? We'll be spelling carrying capacity with a K. All right, now, what we want, what we hope for, is that instead of getting a graph that just grows exponentially, by introducing this carrying capacity, we want to see something that maybe starts growing exponentially, but limits off, right? Kind of slows down, and in fact, approaches that limiting value, that carrying capacity, as time goes on. Because this is much more realistic, right? Now we are seeing that increase in the population, but as the population gets bigger, the growth slows down, right? Our slope flattens. We start slowing down because we can't grow as quickly. We don't have the resources, we're competing, and so on. All right, so we need to somehow change our model so it looks like this. Well, this kind of growth function that actually limits itself has a name, and it's called logistic growth. And if you look at this section, this is section 4.4 in the book, you'll see that it's called logistic growth. And that's just the name for this model. All right, so we need to change our differential equation. It can no longer be y prime equals ky, because that grows exponentially. But we kind of want it to still have that. We want to be able to have exponential growth, especially when we're far away from the carrying capacity, right? If our population is low, there's not competition, right? You have, let's say you have a petri dish, and in it are like 10 bacteria cells. They're not even going to really notice that the other ones are there. They're just going to do their thing. So it should grow exponentially, especially when we're far away from the carrying capacity. But as we get closer to the carrying capacity, we need our rate of change, our y prime, to drop off towards 0. All right, so here's how we're going to build this. We're going to go ahead and start with k times y. That's going to give us our exponential growth. But now we're going to multiply by another factor. And that factor is going to be 1 minus y over k. So it probably seems a little like out of nowhere, this 1 over y minus k, but I want you to think about it. So first of all, notice that if we are really, really far away from y, or sorry, from k, so our y is small compared to the carrying capacity, our population is low. This guy, y over k, is going to be tiny. We're going to be subtracting that from 1. So this new factor I just put in is going to look like 1 when I'm far away from the population, or from that carrying capacity, which is good, right? I want it to look like there is no limiting value on the growth if I've got a really small population. Now, as my y gets closer to k, as my population gets closer and closer to that carrying capacity, notice that this fraction starts getting closer to 1. Well, 1 minus 1, of course, that's going to start looking a lot like 0. So as we get closer, or the population gets closer to the carrying capacity, this gets closer to 0, which means my rate of change slows down. So that's where this comes from. That's why we throw in this 1 over y minus k to make it so that it looks like regular exponential growth if our population is small. And the rate of change in the growth, so the growth rate, decreases considerably as we approach the carrying capacity. All right, so that's where that comes from. Now, before we go and solve this, because we're going to solve this, we're going to see what the solution looks like. I want to talk about this a little bit in terms of equilibrium. So hopefully you remember last time we were talking about equilibrium, and the equilibrium points, or values, those were y values that made it so that our rate of change was 0. And we actually did that by just like looking at this equation and figuring out what makes that 0. Well, you'll notice that this guy y, this leads to an equilibrium value of y equals 0. This other one, we're going to have 1 over y minus k equals 0. And it doesn't take much work to find that that y equals k. So it turns out that that k is an equilibrium value, that carrying capacity. Well, the graph should have tipped you off on that. When we were talking about this last time, we saw that graphs of solutions to differential equations, they end up having asymptotes at the equilibrium, right? The different equilibrium values. And we see that here. There's a horizontal asymptote at k. If I were to backtrack this one, what you would see is it would have a asymptote here at y equals 0. The reason I didn't draw this originally is because if we're talking about a population from here on out, we don't go backwards in time, right? We haven't figured that out yet. For us, time is one directional, so that's why I drew it that way. But if if we extended this solution backwards, you would see another horizontal asymptote at 0. All right, so we actually have two equilibrium values, y equals 0 and y equals k. In terms of what kind they are, the way we can actually figure that out is by drawing the slope field. So let's draw the slope field for this real quick. Now, I know you're probably going, yeah, but we don't have any numbers. Can you give me a K? Can you give me a, let's just think about it generically. And let's just think about pluses and minuses. Okay. So let's start with our population, our Y, being small, but positive. Okay, so ky is going to be positive, and the 1 minus y over k is going to be positive. So we're going to be increasing, but we're going to start small. We're going to start increasing, but eventually we have to slow down because of this factor. So what you would see if you were to draw this slope field, you're going to see flat arrows, fairly flat arrows that are pointing just a little bit up here. You're going to see similar pretty flat arrows pointing up as we are by our carrying capacity. They're going to get steeper and then flatten down again. Okay, so if you wanted to, you could plug in a specific K value. Try to make this look semi-decent. And go do some sort of a grapher and plug this in. But this is what you're going to see. All right, so once we're bigger than 0, we're heading up. Now, if our population gets bigger than K, this guy turns negative. Because now we're subtracting a number that's bigger than 1. So we get a negative times a positive, which means it's pointing down. So bigger than K is up here. We're going to be pointing down, and they're going to get steeper the further we get from that carrying capacity. So now we actually know the carrying capacity. That is actually a stable equilibrium. Remember, stable meant if we step off of it, if we just go a little bit one way or the other, we're going to return. Well, that's what happens with this. If our population dips below the carrying capacity, it's going to grow back up towards the carrying capacity. If for some reason it got above the carrying capacity, it's going to come back down. And that's actually a good thing for this model. That totally makes sense, because think about this. If we have a limit on how many, let's change, we've been talking about Petri dish. How about we get a number of coyote that live in the Tahoe Basin? There's going to be a cap on how many coyote can be there, right? There's only so much feed for them. If for some reason we introduce more coyotes than the carrying capacity, they're going to starve. They're going to be fighting for resources. There's not enough of them. Some of them are going to die off. So that population is going to drop back to the carrying capacity. So this is like beautiful. It does exactly what we want it to do. Now 0, we don't usually think about 0 so much in terms of what happens on the other side, because if we're talking about populations, negative populations don't really make sense. But even just think about 0. If we were to step off from 0, what's going to happen? Well, our slopes are all pointing up, and we're going to move away from 0. So 0 isn't stable. Turns out that this is an unstable equilibrium. And you would actually see if you went negative, if you went down to a negative y, you would actually see with the slope field, you'd see those start pointing downward. So they're both pointing away. So it actually is unstable, not semi-stable. All right, so a much better model. It fits population dynamics much better. And remember the whole goal, well, maybe you don't remember, but the whole goal of calculus, I know you probably think it's to torture poor students, but no, the whole goal of calculus is to create math that we can use to help describe what we see in the real world so that we can do the math on it, make predictions, and so on. And so this definitely fits the real world much better than plain old y prime equals ky. All right, so cool. There's our differential equation. It's gonna be a initial value problem. You'll always have your initial population, right? So it won't just be the differential equation. You'll end up having some sort of a y of 0 equals, I'm going to be really boring and call it y naught, but there will always be something here too, right? We're going to know how many coyote are in the basin because we went out and we did a study. We're going to know how many bacteria are in our petri dish because we counted them. We're going to know how many fish are in the lake or whatever it happens to be. We're going to have our initial value. All right, so that's going to actually let us find the particular solution. It's going to give us our starting point, and then we just follow the arrows and approach carrying capacity. All right, so let's do it. Let's solve this bad boy. Now, there's going to be a lot of algebra. I'm going to warn you up front. There's going to be a lot of algebra, but if you follow the algebra, you let it run its course, we're going to get a good solution. You're going to see that the calculus is terribly easy for this thing. It's the algebra that's going to get us. All right, so strap in. Realize that this is a video, so you can watch it over and over and over and over. So you can go back and you can try to catch the algebra steps that you missed, right? Since you're not here to ask me. And I will do my best to not make any mistakes. Ooh. Good luck with that, right? Okay, so if I make a mistake, I apologize ahead of time. I'm doing this live, one take, right? We're just gonna go with it. All right, so we see that it is separable. Hopefully, hope that you see that it's separable. What I'm gonna do first, just to make life easy. Oh, I just realized I have 2 Ks. I meant for this first one to be an R. Look at that. My first mistake was even when I first started. We want R times Y. Can't use K because that's K. So again, what R is, this is the growth rate. K is the carrying capacity. Okay, so this is what we're going to go with. We're going to start with this guy, and we're going to solve it. So first things first, just to make life a little bit better. I'm going to pull this K out. Basically, I'm going to get a common denominator, and I'm going to pull the denominator out because I don't want it in this factor. It's going to make it a lot harder when we go to do the integration. So just by a little bit of magical algebra, we get R over K times Y times K minus Y. And again, the behind the scenes step was get a common denominator here, K over K. So you can see the K minus Y, all over K. I just brought that K out. All right, so now let me separate it. So I'm going to get dy over y times K minus Y equals R over K times dt. So the y prime, I made it a dy dt. I'm going to use t instead of x for time, right? So we're going to be looking at population with respect to time. You're not comfortable with that, make it an x. I don't care. I'm just going to use t. All right, so it's separated, which of course means the next step, let's integrate. So we're going to integrate both of these sides. Now, the R over K, easy. Easy, easy. That's a constant. That's all constant. This is your growth rate. That's your carrying capacity. It's constant. It's going to be that times. This one, we're going to have to do partial fractions. So let's set ourselves up. Let's do the partial fractions up here. We're going to have A over Y plus b over k minus y. It's already factored for us. They're both linear factors, so we just have constant. When we put that together, we get a times k minus y plus b times y. And that top is going to have to equal 1 because we had 1 dy on top. All right, well, let's plug in some values. So I'm going to do this. I'm going to start with y equals 0 because I like y equals 0. This is going to give me a times k. So a times k plus 0 equals 1. So that means that a is equal to 1 over k. Cool, that was nice and fast. And then I'm going to plug in y equals k. So I get a times 0, that's gone. B times k equals 1. So it turns out that b is also 1 over k. So that means, remember this fraction right here is we're breaking that apart. What we now have is 1 over k times 1 over y plus 1 over k times 1 over k minus y equals rk. So I just split that guy apart. Well, before we integrate, I'm going to do one more thing. Notice that there's a k everywhere on the bottom. I multiply by k, all that stuff is gone. So it turns out what we're going to integrate is a nice and easy 1 over y plus 1 over k minus y. And on the other side, we're integrating r. So I'm just going to stop here for a second, catch our breath, and just point out that we just did a crap ton of algebra. But that algebra got us to a point where the integration is going to be crazy fast and crazy easy. All right, so that's one of those things. We're willing to, hopefully you're willing to do a little bit of algebra work to make your calculus easy. All right, so when we integrate this, 1 over y, of course, gives us natural log of y. The 1 over k minus y is going to give us natural log of k minus y, but a minus sign from the chain rule. And then on the other side, we're going to get RT plus C. So pretty fast, pretty quick. Well, now here comes a whole nother boatload of algebra because I want to solve this for y. All right, so here we go. First things first, I've got one log minus another log, so I can combine that into 1. So that's going to be the natural log of y over k minus y. It equals RT plus C. Now I'm going to change this to exponentials to get rid of the log. So it's going to equal e to the RT plus C. But hopefully you guys are good with me doing this. We've only done it a million other times. I'm going to just write that as C e to the RT. So this is a new C. Another arbitrary constant is actually equal to e to the old C. Again, arbitrary. Who knows what that doesn't matter, so I can just name it itself. All right, well, now I got to get rid of the fraction. So I'm going to multiply both sides by k minus y. So that's going to give us y equals ck e to the RT minus cy e to the RT. That's been distributed. Now I need to move both of those y pieces together. Move that guy over here. So I'm going to get y plus cy e to the RT equals ck e to the RT. I'm going to factor out my y. So I've got a y in both of those. And then I'm going to divide by that factor. I don't know. Hopefully that wasn't too bad, but we used a lot. Used a lot of algebra. Now I'm going to do one more thing just to make this a little bit nicer still. I'm going to divide out that c on top and bottom, just so I can get rid of it. So what that's going to give me is k e to the RT over 1 over c plus e to the RT. And since c was an arbitrary constant, 1 over c is an arbitrary constant. So I'm going to pull that same trick again. I'm just going to rename that c. So this c, this is like the third c we've run into, right? This one is 1 over the second c. The second c was e to the first c. Whatever. They're arbitrary constants. It doesn't matter. All right, so here's where we end up now. We've got y equals k e to the RT over c plus e to the RT. So that's what this solution looks like generically. But let's go ahead and get a initial value, or let's use the initial value. So if we bring that back, remembering that the initial value was y of 0 equals y naught. If I plug that in here, I'm going to get y naught equals k times e to the 0 over c plus e to the 0. So those e to the 0s are 1s. What do we get here? So I need to solve this for c. So I'll just do a little cross multiply business. And so then c is going to equal k over y naught minus 1. All right, so let's put that in here. So we have y equals k e to the RT over k over y naught minus 1 plus e to the RT. And we're almost there. I'm just going to do one more algebra step because I really don't want fractions inside of fractions. So I'm going to multiply top and bottom of this by y naught. Okay, so now this is when we need the drum roll, because we're at our answer. The solution to logistic growth is going to be y equals k times y naught times e to the RT divided by k minus y naught plus y naught e to the RT. So we'll go ahead and put a box around this, because we actually have our solution now. And you want the good news? I know at this point you're probably like, there's no good news here whatsoever. Your brain's probably bleeding out your eyes because of all the algebra. But here's the really good news. You never, ever have to solve another logistic growth problem ever again. We just solved every single one of them. Every one of them. It doesn't matter. Because look at what this requires us to know. Again, K, that's our carrying capacity. So if you know K, you're gonna put that right in these two spots. Y naught, this was our initial population. So just put your initial population in there. And then the only other thing was the R, And this was your growth rate. So literally all you got to do is punch that stuff in here and you got your solution. So I know it doesn't really feel like much of a good news kind of situation. You notice I didn't give you any bad news either. There's no bad. No, it's good news. I mean, yeah, we did a lot of algebra, but that's why we learned algebra, so that we could do stuff like this, so that we can get one answer that always works for anything that's modeled this way. To a mathematician. Actually, to scientists should be really happy about this too, because now going forward, you can just plug and chug. And scientists love to plug and chug. Trust me. All right, so let me show you how easy this is given a situation. So let's say we're looking at the coyote in the Tahoe Basin. And so we go out, we do a study, and we actually count how many coyote there are, or at least roughly. And let's say that we count that there are 1,000 coyote throughout the entire Tahoe Basin. So South Shore, North Shore, like everywhere. All right, so here's our example. There are 1,000 coyotes in the Tahoe Basin. All right, so the basin can, or how about the basin has resources, or has enough resources for 10,000. All right, so if nothing else, I mean, there could be 10,000 coyote. All right, and then we determine that the coyote population has a growth rate of, let's say, 2%. Here you go. We're going to build a model showing the population of the coyote. So we're going to have y equals the k, 10,000, times the initial population, 1,000, times e to the rt. Okay, well, r is 0.02 e. All right, in the denominator, we need to do k minus y naught. All right, well, that's just going to be 9,000. All right, so our carrying capacity minus the initial, plus 1,000 e to the 0.02 t. Now, I am going to simplify this because I can divide everything by 1,000. But we end up with y equals 10,000 e to the 0.02 t divided by 9 plus e to the 0.02 t. And that right there, ladies and gentlemen, is the function that's going to model our coyote population. So if you want to know how many coyote are there going to be in 10 years, plug in 10. How many coyote in 100 years? Plug in 100. In a million years? Well, that's probably going to be 10,000 once we round it. But what we'll see with this is that it's going to start growing exponentially, but then flatten out as time goes on and it approaches our carrying capacity. All right, so there's logistic growth. That's all this is. We're now instituting there's a limit that we can't go over, or if we do go over, we're going to cut back down. All right, so it's just another application of separation of variables. Now, I don't want to go too far into this because now if we want to talk population modeling, this is like, you can have classes on this. Because like, think about this, even this model, it's not really good. I mean, there are other things that we have to worry about. I mean, think about coyote, for example. The population of the coyote doesn't depend on just the population of the coyote. I mean, even if we eliminate like the human factor, which trying to deal with that is crazy. Just think about this. Coyotes got to eat, right? Well, coyotes are going to eat, rabbits and squirrels and things like that. So the population of coyotes is going to depend upon, say, the population of rabbits. Well, but the population of rabbits depends on the population of coyotes. Right? If there are a lot of coyotes, they eat up all the rabbits start dying. Well, the rabbits start dying, the coyotes start starving, they start dying. Well, fewer coyotes mean the rabbits can start reproducing more and more rabbits, and they start increasing. More rabbits mean more food for coyotes, they start getting bigger. More coyotes, oh no, now the rabbits are dying off, right? And so you can create what's called a predator-prey model. To solve that one, you guys need considerably more math. You're going to need a lot of the math you get next year, linear algebra, and also in differential equations. We get what's called a system of differential equations that requires using eigenvalues of matrices. And I know I'm starting to say things that you're like, I have no idea. Next year, this time, you'll start understanding. So that makes it more complicated. Even if we don't have a predator-prey thing, something that would be more realistic also is what we call a threshold. Now, a threshold is kind of like a carrying capacity. It ends up being an equilibrium, but it's one of those things that if you are below the threshold, you die out. So think about populations. It kind of makes sense, right? If the coyote numbers drop to too small of a number, that population is going to die out. There aren't going to be enough breeding pairs. The males and females aren't going to be in close enough contact to breed. Right? The population is going to die. I mean, that's what happens with a lot of extinctions with animals. Population gets too low and then they just can't recover. So you could introduce a threshold. Right? Well, that's going to complicate things too. It's not terrible. Let me show you what that looks like actually. First of all, on a graph, what I'm talking about, if you look at population versus time, again, there's going to be your carrying capacity. Call that guy K. But there's also going to be a number down here called the threshold. So that if we're below the threshold, like if our initial value is down here, we're going to drop off to 0. We're going to die out. If we're above the threshold, but below the carrying capacity, we want it to do basically what the logistic model did. And if we're above the carrying capacity, we want to drop back down, right? So this is what the picture should look like, the slope fields and all that. In terms of what the differential equation looks like, you started off just like one with the carrying capacity. So you'll have y prime equals ky, ry times 1 minus y over k, right? That's what we just saw. But then we're going to introduce a threshold. So we're going to do the same thing where we make a 1 over y minus t. But to make it do what we need it to do, because we added in another factor, we actually have to make this a minus. It just makes it so that the signs all work out. But this is now the differential equation for this model. It's still separable. You can still pull all that y stuff onto this side and the dt over there. It's just now got 3 fractions. So when we do partial fractions, we're going to have 3 pieces. You can build it. You can go through all the algebra. You're going to get logs that you can combine, turn into e's. Right? I mean, you'll get there. We're not going to touch it. But you can kind of see now the idea, though, that we can make these models do just about anything we need to make it realistic. It's just as we add in more of those restrictions, the math gets more complicated. Right? I mean, just go back to y prime equals ky. That was easy. That was a super easy separable differential equation. We had no problem getting y equals ce to the kt. But then we started going, well, but that's too simple. Let's put in more reality. The math got harder. We're still able to do it, but the math got harder. We added more reality. The math gets harder. We can still do it, but it's more difficult. Add in predator prey. Whoa, the math gets harder, but we can still do it, right? And that's a big thing that happens in science, by the way. Like when you, a lot of you are taking physics right now, I know, and think about this. When you talk about this pen flying through the air, you always ignore air resistance, right? We're going to ignore air resistance, but we know that that's horrible because air resistance matters, right? If air resistance didn't matter, when I drop this piece of paper, it falls as fast as the pen. Right? Why didn't that happen? Air resistance. But the reason we don't do that to you right away is adding air resistance makes the math that much more complicated. Right? And in fact, the first thing that you do when you introduce air resistance, you need differential equations. Right? And that's even an oversimplification. So really what happens is the more accurate you want it to be, the more realistic you want it to be, the harder the math's going to be. And I'm just shooting straight with you. You know, I'd love to sugarcoat it, but no, that's just how it is. All right. Well, anyway, so take this for what it is. It's just another application of differential equations that leads to separables that we can solve. It just ends up being a more realistic model for population growth. All right. Well, I think we'll go ahead and wrap this up. So I hope you enjoyed our first ever Calculus at Night video edition. The plan, if you're watching this, just so you know, again, on Monday, class at the normal time, doing the normal stuff, but we're gonna really review for the final exam. All right. So with that, I hope you guys are having an awesome weekend, a great day, whatever time you're watching this, and I will see you all Monday morning. All right. Adios.